Welcome to Engineering Statics. This is ENGR ampersand 214 at Bellingham Technical College. In this lecture we dive into the analysis of equilibrium. And this is basically the heart of statics. This is where we look at which combination of applied loads, both contact point loads and distributed loads, applied moments, couples, that will result in your rigid body not accelerating. So we're going to look at all of the strategies necessary to ensure and be able to verify that the sum of the forces is zero in every orthogonal direction and the sum of the moments is zero in every orthogonal direction, because that's the criteria for non-acceleration or static equilibrium. So we're going to start out with a few more definitions. Some of these we've worked with in the past, but we're going to formally define them and then use their full definition to our advantage in analysis. So we start with loads. Loads are applied forces, and so this encompasses both a point force, so like a contact point load, or a distributed load like gravity or pressure. We can have reactions. So these are the responsive forces from support structures, maybe a substrate, the ground, that are necessary to maintain static equilibrium. So for instance, if you stand on the ground, your weight is an applied distributed load that can be said to act at your center of mass. And if you're standing with your feet on the ground is reacting against your feet and probably pushing upwards vertically, and if you're not sinking into the ground, the reactive force, or the normal force usually called, of the ground is equal to your weight. We can have reactions that apply torque to resist twisting or turning or flexion, and in fact we will have a whole section on the different types of reactions and particular devices that are designed to provide them. The concept of a rigid body. All statics generally deals with rigid bodies. We don't analyze the effect of our loading on a body's deformation. So we don't look at stress and strain or plastic flow in statics. We just look at our forces and moments balanced so that we are in static equilibrium. A body that, a part, an object that allows you to do that without having to consider deformation is called rigid. You can think of it as having basically an infinite modulus, and you can describe rigidity mathematically by requiring that the distance between all pairs of points remain constant with loading. So if you have 2 points on a body, you have a 3D body, and you have one point at coordinates x1, y1, z1, and you got another point somewhere else. We'll call it x2, y2, z2. We can apply a load, and the distance between those points doesn't change. And if it doesn't change, we can say that the body didn't deform. It didn't stretch, it didn't shrink, it stayed exactly the same shape and size. So shape and size both are important for being rigid. In the real world, of course, nothing has an infinite modulus. Even the most rigid materials like carbon fiber and tension or certain ceramics, everything has a finite modulus in tension, compression, and shear. So rigid bodies are ideal, like ideal fluids. They don't really exist. However, if we are looking at very, very small deformations, we can approximate most things as rigid bodies. So basically, it depends on the load versus the modulus. And most applications you don't, if you plan for it. Certainly, as we get into more complex designs, we'll start looking at that, and that is exactly what you pick up in the study of mechanics of materials. So, but that is next. And even when you do consider that, first you have to look at things in static equilibrium. So that brings us to the equations of equilibrium. They apply to everything, and it's important to know that you can have something that's not rigid, like some piece of putty or something. You can put that in static equilibrium. So its entire body, its center of mass, for instance, is not accelerating. It's not undergoing rotational acceleration. It could still deform. So it doesn't have to be rigid to be in static equilibrium. So what we're going to look at from here on out in the class doesn't necessarily have to apply to a rigid body. The bodies we will consider are. The important thing is that the sum of the forces and moments in every orthogonal direction is always 0. Otherwise, we are in dynamics, which is another class. Okay, our most valuable weapon for determining equilibrium states and what is necessary to keep something in static equilibrium is called a free body diagram. This isn't just a sketch with arrows on it. This is a very specific tool that we use to determine all the forces and moments that are acting on our body of interest, not necessarily all the other bodies around it. And it's basically an application of Newton's second law in a lot of ways. And the easiest way to look at that is to do a quick example here. So this little sketch, very crude schematic, is of a person standing with both their feet at the end of a diving board. It's the length B. It's kind of held up with a fulcrum that doesn't have a hinge. It's just a point support. So this is a support, so it's going to provide a reaction to the board. And it's at distance A from the hinge, which we call point O. And there's the water under the guy. So we're gonna use free body diagrams to express the sum of the forces on the diver, the sum of the forces on the board, and the sum of the forces on the diver board combo, and look at them all independently, and then find out what's common to them. And we got some data that we're given about the diver and the board. The diver has a weight of W sub D for weight of diver, and the weight of the diving board is W sub B, meaning weight of the board. And we're going to assume that the diver is standing at the very end of the board. His feet are actually pretty close together. Okay, so we're going to start with a free body diagram of just, we're going to start with the board and the diver, excuse me. So we're going to start with a combo. So we're going to do 3. The board by itself, the diver by himself, and the board diver combo. So this is the whole body FBD. And for this, we're going to assume that the diver and the board are kind of one big body. It's almost like one big blob here. We're not going to look at anything between the diver and the board because we're looking at one body. So we're going to draw the forces that are being applied and the moments, if there are any independent moments, that are being applied to this whole combo. Okay, so remember we had a hinge over at point O. A hinge doesn't apply any moment. It doesn't twist anything, at least in the plane that we're looking at. It does in the other 2 orthogonal planes, but it doesn't resist twisting around its own axis. So in this XY plane, there's no moment being applied by the hinge. There is an upward force, and we'll call it O sub Y because we'll say Y is in the vertical direction here, and O sub X in the horizontal direction. It could apply those. Whether it is or not, we don't know, but it could. So we're going to put it down, and then we're going to solve to see what it is. A sub Y represents the upward force of the fulcrum here, because it's pushing on the bottom of the board. And then we have the weight of the board acting at its center of mass, and the weight of the diver acting kind of at the end of the board, which is kind of represents the center of the mass of the diver. Okay, so the weight of the board force. So what we did was we resolved a distributed load of the board weight, and we put it at what we knew was the center of mass. So we did a kind of a by observation force resultant for the weight of the board, and we stuck it in the middle because we are assuming the board is uniform density. Okay, so important things. Do we have all the forces? We have a support reaction and another support reaction, and we have the board weight and the diver weight. There were no other loads. Wind wind isn't pushing anybody sideways. There's no downward forces of water pouring down on somebody. There's no other contacts to transmit force. So we have all the forces, and we have them in the right place. We said the diver standing way at the end. We've got the board weight in the proper position at the center of mass. A was the distance of the fulcrum, so we have all the forces and all the moments. There were no moments, as it turns out, and they're all in the right place. Great. So with this, we can basically write are equations of equilibrium. And this is the heart of putting something in equilibrium, is adding up forces and moments. Okay, so we got a 2D problem, so we're really only considering forces and moments in the x and y direction. There's no z, so we only have 3 equations of equilibrium. So we're going to say, if I want the board diver combo body to be in static equilibrium, the sum of the forces in the x direction better be 0. Well, the sum of the forces in the x direction is just O sub x, the x component of the force of the hinge. There's nothing else. So if we're in static equilibrium, we know right now that O sub x would be 0. Okay, so we got 1 down. We know that the sum of the forces in the y direction has to be 0 if we want to keep things in static equilibrium. So, okay, let's tally them up. We got O sub y going up, we got A sub y going up, we've got W sub b going down, and we have W sub d going down. So if we wanted this body, this board diver combo, to be in equilibrium, this would all equal 0. Now for the trickier one, the sum of the moments. And you got a choice now. You can add up the sum of the moments about any point in the body to show that that body is in equilibrium from the standpoint of 0 torques on the body. It doesn't matter what point you take it around, and that has to do with our some of the properties of moments that we've calculated earlier with some of our mathematical proofs. So that's nice. You can pick any point on that body and write an expression for the total moments about that point. And remember, moment about a point is every force crossed into, or every radius, excuse me, crossed into the force, looking at the line of force and the radius from the point of interest. And then if there are any direct couples that are being applied, you add those in. So let's see what they are here. I've decided to take the moments about point O, because if I do, I have a concurrent force system. O sub x and O sub y both converge on point O, so they can't produce a moment about that point. So I kind of eliminate those from my mathematical equation here and make it easier to solve directly for something. So I decided to take the sum of the moments about point O. So if I just use my cross product relationship, I will have the radius A times A sub y, and using my right hand rule, that would produce a positive moment coming out of the page. I've got a negative moment of B over 2 crossed into WB, which is just B over 2 times WB, and that's negative. So that's creating a moment that would be oriented into the page. And remember, moments are vectors. So you would write those with a double-headed arrow, or an arrow with a turning indicator around it. And then the moment from the diver is the full B crossed into WD, and that's also going into the paper. So that's the sum of the moments about O. So that's everything I can say about the board diver combo. I can't say anything about, what's going on between the board and the diver. So if I wanted to do that, I would have to do a separate FBD for the board. So in that case, I would just sketch the board. I've got the same support reactions from the hinge and from that pin support, the fulcrum, the same position. I've got the board weight alone going downwards, and I have some force P coming from the diver. Now at this point, I don't know what that force P is, basically. I had it up in here because I knew what the weight of the guy was, the diver. But if I'm just looking at the board, I don't necessarily know what the weight of the diver is yet, if I started here. Furthermore, maybe the diver's carrying something that weighs something, or maybe the diver is suspended with a harness system that's taking up part of his or her weight. So this P would not necessarily be the weight of the diver. I don't know that yet, just from this FBD, but I just know there's a load here, which is a contact force being exerted by the diver. and we don't know what it is at this point. Otherwise, we can go through our tally. Same sum of the forces in the x, O sub x, nothing else. Sum of the forces in the y, O sub y going up, A sub y going up, W sub b, board weight, going down, and P going down. And then moments are going to be the same as the previous expression, except this time the force at length radius b is just our P. Now, if I want to relate P to what's going on with the diver, I have to FBD the diver, just the diver. So I got to look at all the forces on the diver. Well, I'm going to assume the diver's standing on 2 feet. And if it's just the weight of the diver, if there's not a rope pulling him up or he's not carrying anything pushing him down, there's just the weight of the diver. And of course that would be balanced by, if he's standing evenly on both feet, an upward force of P over 2 on each side. So P equals WD. And so that would give me a WD back in here and allow me to solve for everything. And again, if you didn't know, you would get the reaction force as a function of WD and anything else that's going on with the diver only in the diver FBD. You wouldn't necessarily know that up here. An important thing to notice, kind of panning back, and I'll kind of scan out a little bit, we had 1, 2, 3 FBDs, and we produced 1, 2, 3 sets of equations of equilibrium. Typically, depending on how many unknowns you have, you may only need to use 2 out of the 3, all but 1 of your FBDs. 1 will be redundant, and you can use that as a check. So that's not always true, but it is quite often. So if you end up with that extra FBD that you didn't use, go ahead and write your equations of equilibrium for it, and then you can get a check on your previous calculations. Okay. One thing to notice here, when the action-reaction principle, we just invoked Newton's third law, whether we realized it or not. We're looking at the pressure or contact force of the diver on the board. Given that there are no other forces in this particular scenario, there's no ropes around the guy, he's not holding anything, his weight is basically equal to the contact force. So he's in contact with something, and those contact forces are basically equal and opposite. So you notice that we've got an upward force of P from the standpoint of the diver, but we have a downward force of P from the standpoint of the board. Now, those types of contact action reactions are very, very common in equilibrium analysis, especially with trusses using the method of joints, looking at pins on their hinges. So that's important to keep the signs straight. The direction of force A on body B is going to be opposite from the effect of body B on force A. And so you're just, if you remember Newton's third law, equal and opposite, you'll get that sign right. Okay. Speaking of which, how do we transfer force by contact? Since that's really what Newton's third law is about. When we push on something, how can it push back? Things can push back different ways, and depending on the type of interbody connection that our parts have, we can provide force or moment. Moment also being called a couple, and you'll see the letter C being used for moment on this page, and that just means we're using the term couple, which is pretty much equivalent. We can push back with a force or a moment in either 1, 2, or 3 orthogonal directions, depending on the type of connection. And lots of standard parts are built specifically to do that. So we'll use these a lot in our beam truss frame and machine analysis. So we're going to go down through the general categories and just give a few examples of typical parts that would provide this. So we start with what's called a general interaction, and it's a type of interbody connection that provides the most constraint. And in order to provide the most constraint, it provides the greatest number of forces and moments. So this kind of interaction will give you a pushback force in all 3 orthogonal directions, and it'll apply a restraining moment, couple, or torque in all 3 directions. So it basically doesn't allow movement. It doesn't allow movement anywhere or any twisting, and so totally constrained. And a weld or a very effective adhesive would do that. That's an example of a practical general interaction. Stepping down, we take away one element of constraint, one CZ. You get something that can apply forces in all three directions and moment in two, but it allows rotation in around one axis. So there's one axis free that there's no moment applied for. And an example of that is a door hinge, something where you've got an upset, a head on the end of a shaft that's restraining in one direction. You can't flex in either direction, but you can rotate in one. If we go one step further and allow motion along the axis and rotation around it, you've got a sleeve, no thrust support, so there's no head on the pin. So like a shaft in a bearing could move axially, parallel to its axis, but that bearing is restraining it kind of radially in the two orthogonal directions perpendicular to its axis, and it's providing restraining couple or restraining moment in every direction other than the axis of rotation around the axis of the part itself. So notice we're going from high constraint to low constraint. A pin in a slot, that can move freely in two directions and can rotate in two directions, but can't. There's only one direction where it can't move. Ball and socket, forces applied in all directions, no moments. It can twist, it can flex, and twist in all three directions. And a ball bearing, like a bearing race, would constrain with force in two directions. It could move in one direction, like along an axis, like a bearing. The balls could roll down a shaft, and no moments. So there's a roller or a ball bearing that can rotate. Roller bearings, you have little pins all the way around. They're like a ball bearing in terms of forces, but they're going to act a bit like that sleeve bearing and prevent something from flexing around itself. And cables are really special because they only apply force in one direction at a time by definition. No moment, no forces in three directions. They can only pull, or they can't push either, actually. It's one way and in one direction only, and that's something that's used to advantage in cable analysis. It simplifies the analysis in a lot of ways and makes it possible. Okay, so those are all the ways that something you're contacting might push back or twist back against you. So depending on the type of connection, and there's standard symbols for them that we'll look at, we will slap down forces or couples to correspond to that type of connection and then solve for what they are. But if we know the type of connection, we know to at least represent, put a placeholder force that will go into our equations. So we have a little FBD checklist to make sure we've really done it properly and we can use it to write our equations of equilibrium. So step one, catalog all the external forces and couples acting on the body. And this includes distributed, so your weight, pressure coming from something, a wind load, those are all external forces. If you miss a force, you will get your analysis wrong. And it's really easy to miss little ones. So, look at your schematics carefully. Read the description of the problem very carefully to make sure you're not forgetting something. Okay, next, you graphically display direction and locations, lines of action, locations of contact of all of the unknown reactions. So you're going to put down your applied forces, where they're acting or their lines of action, and then if you have supports, a hinge, a pin, the ground, anything else that's resisting those forces, you add forces that represent those, and locations very important. So here's where you want to read the dimensions of your part very carefully. Make sure you're getting angles right, lines of action right, And I guess that's number 3. Geometric dimensions are needed, especially for establishing moments. You may just be able to go with orientations of forces and adding them all up, get them, resolve them in the orthogonal directions and get your force balance. But because moment as a result of forces is of course r cross f, you need the dimensions of the part to get r. Okay. So once you've got all that, you use your FBD to tally forces and moments, and you'll sum all of the forces in every orthogonal direction, x, y, and z. Phi, rho, theta, if you want to use spherical, we'll use Cartesian in this class, and set them all to 0. So the force results into 0, and you'll take the sum of the moments about P, which is any point, and set it to 0, and solve for what it would take for these sums to be true. So a lot of times you'll be asked, what is the force, magnitude of force, or what moment or at what point would this force have to contact something such that it would be in static equilibrium. So you write your equations from your FBD, which contains that unknown, and then just set those sums equal to 0 and solve for your unknown. Needless to say, you can only solve for the number of unknowns for which you have equations of equilibrium. So if you got 3 unknowns in a problem and you've got a 2D problem, you're going to have 2 equations for force reactions and 1 for moment. So you better not have more than 3 unknowns. Otherwise you won't be able to solve for them. And they have to be truly independent equations and not redundant. Okay, so we will do a quickie example. So we got a block here, and it's got a little ring on the top. And so you've got a cable that's suspending the block between a vertical wall and this middle of the block, and then a vertical wall. And the cable's 2 is coming off at 45 degrees to horizontal, and cable 1 is coming off at 30 degrees. So, and these are cables. They can only pull, and they can only pull in the direction of their orientation. And there's 2 of them. They're fixed here. It's not a continuous cable. Okay, so here's our FBD. We've got a little sketch of the block. We've got tension of cable 1 at A at 30 degrees, and you've got another cable, T2. Had it been one cable, it would have had a single tension, but it's a different cable, so it's got T2 at 45. The block's got a certain weight, and it's acting at the center of mass of the block, and we're going to assume from the way our schematic was drawn that A is coincident with the center of mass. So those are in line basically. So we can use some trig. Let's check. We've got all the forces, weight of the block, tension, they're drawn in the right place. Okay. So let's write an expression for the sum of the forces in the y. We have the y component of T2, which is magnitude of T2 times sine 45. Going up, we've got the y component of T1, which is the full magnitude of T1 times sine of 30, which is 1/2. And this should be a 30 here. This was miswritten. And then you have W going downwards, so that's a negative. We'll set that equal to 0. That says the sum of the forces in the vertical direction is 0. Take the sum of the forces in the x. W is pointing straight down, so it won't be in that equation. We'll take the x component of T2, which is T2 times cosine of 45 degrees, and then the x component of T1, which is the full magnitude of T1 times cosine of 30. And that's written correctly. And they are pointing in different directions. A helpful thing to do is to slap a coordinate system on your problem before you start. That gives you a consistent reference for signs. So here's upwards, positive y is going up on the paper, and positive x is going to the right. So T1 was positive, T2 was negative in the sum of the forces of the x. I could actually prove that if this is hanging, the sum of the moments about A would have to be 0, which means that a radius from point A to the center of mass of the weight crossed into the line of action of weight, which is vertical, would have to be 0, which means the angle between these two has to be 0. So my moment equation in this case really doesn't give me any information. So I've really only got 2 equations that I can use for equilibrium analysis, so it's a good thing I only have 2 unknowns. So I use these 2 equations and solve for the 2 unknowns, just use some algebra, and I can get values for T1 and T2 in terms of W, the weight of the block. Okay, we are going to stop the lecture now and resume with this fairly complicated analysis of a flag. This is 3D, and there are a lot of moments in various different directions and forces, so this is a great example of looking at breaking up a problem into multiple free body diagrams, but it is basically uses exactly the same principles that we did in this simple hanging block. So we'll see you next time for that.